Hello and welcome back to the lab. Today on the bench, I'm going to attempt to demystify some of the previous videos, scope alignment videos, things like that I've done. And I've been having some discussions with a couple of people about square waves, bandwidth, rise time, and how all this stuff kind of comes together. So this is going to be a pretty dense video. Not that my videos aren't dense to begin with, but this one's going to get into some theory and also some practice with various waveforms, and hopefully it will also help answer some of the questions that I've been getting about, can I use a function generator to calibrate an oscilloscope? I do have a video on that coming. For those who haven't seen what's kind of happened to us in the last, year and a half now. We've had some vehicle problems, and it's been one thing after another. But we are recovered from that, so I appreciate everybody's support and well wishes. But we are moving forward, and things are looking up significantly. That being said, I haven't gotten a chance to get the function generator I need to do that video, so it is in the works. I have not forgotten about it. Life has just mildly gotten in the way. I am coming up to a point where that is one of the next few things that I'll be acquiring for the lab is that function generator. And this particular graph goes very deep into why I'm struggling with the function generators I'm picking, and where pretty much every function generator non-specific signal source is going to kind of fall on its face. These are some cutaways of two different square waves, and the important thing there is to note the rise time. The rise time of the signal is from when 10% of the final amplitude, 90% of the final amplitude. This space here is the time it takes to go from here to here is the rise time. To make a square wave, a whole bunch of sinusoidal waves are overlaid on each other. Tektronix themselves actually put out a good video that the Vintage Tech Museum posted. I'll leave a link in the description for more information on square waves. But the square wave itself is harmonically rich, and another way of looking at that would be it is a high bandwidth signal. This has nothing to do with the rep rate, how fast the pulses are coming. This has to do specifically with the rise time. The more harmonics we get to overlay to create the square wave, the steeper this rise is, the faster we go from 10% to 100%. The importance of that is it allows us to test things like amplifiers, filters, things like that, because there's so much harmonic content in a square wave. Seeing what comes through on the other side, we can see what the filter's doing. I could have I could feed a square wave into a 10 megahertz bandpass filter, round off the edges, and get a 10 megahertz sine wave out of it because I filtered everything else out. That works. It's not distortion free by any stretch of the imagination, but it does function. A lot of the function generators that I've seen people try to use to align and calibrate scopes don't have a steep enough edge, and that's the problem. Is when you're doing the high frequency calibration of an oscilloscope, this edge should be as clean as possible. It should be as steep as possible. So this would be a very poor square wave. This one would be better for aligning the high frequency chain of a scope. Really what we're doing when we're dialing in the high frequency area of a vertical plug-in is we're looking at, we're adjusting the capacitances to balance out some of the parasitic inductances and resistances, because it's all the it's all the RLCs kind of adding together, and we want that to be as smooth as possible, but still get the rated speed. We can make perfectly nice square waves, but we'd tamp down the bandwidth of the plugin too much, and it would kind of be lackluster. Let me get a vertical. Here we have the vertical section of an oscilloscope, and we have the input attenuator, which is kind of how Tech did their scopes. It's much easier to make a high bandwidth amplifier if you have a fixed gain. If you try to make one variable gain, it gets very difficult very quickly. So that's why the way Tech did it is they attenuate the signal so they have a fixed signal here that they then have a fixed gain amplifier, and then it gets to read at on the display of the scope. Now the calibration points are these RC networks right here. So here's one for this amplifier, here's one for this amplifier, here's one for that amplifier, and here's one for this amplifier. And actually this one has two, so it's here, and then they also have one here, and the same thing for the first amplifier. So what we're doing is we're balancing the RC networks for the individual amplifiers to get the fastest rise time with the cleanest square wave. And it is a balance. We could get crazy fast rise time, but then we have horrible looking square waves with lots of ringing, all kinds of craziness. So it's not a good representation of the signal. We feed in a clean square wave and it looks like crap on the screen. So the other thing is these RC networks, because they're filters, they're very sensitive to these capacitors going open. I have seen scopes, and I've helped other technicians with scopes, where they've been down 60 megahertz on bandwidth, 100 megahertz on bandwidth, because some of these trimmer capacitors have opened up and they're no longer acting as capacitors, they're just open circuit. So the rated bandwidth of the scope is very sensitive to this configuration, and that's why you'll see in some of the videos, especially some of the 400 series and a couple of these, is I'll do the alignment, I will then do a bandwidth check, I'll probably be a little low, little light on bandwidth, and then I'll go back in and do it again, and then I'll peak up the waveform a little bit, and then it'll I'll have the rated bandwidth of the scope or a little bit more. Cranking this up to way over the rated bandwidth of the scope isn't a good idea either, because you lose the fidelity of the signal through the amplification chain, which would be undesirable for a measurement device. You want it to have as accurate a representation of signal as possible with the steepest edge and the cleanest corner. And that's where we get into some kind of crazy specifications of square waves that I have in the lab. So my fastest square wave in the lab is the 284, which is so fast at 70 picoseconds. So this rise time up to here is 70 picoseconds, which is incredibly fast. And it's so fast I'm having to get, I exceed the bandwidth of all my scopes, including the DSA, and it's kicked me into the 11801, which is a sampling scope that has a rated bandwidth of 12.5 gigahertz. Now, fortunately, the 11801 is a voltage limited scope because it's so fast, but the 284 actually doesn't put out that much amplitude, which is something you'll find with extremely fast edge signals, is due to physics limitations of the slew rate, where how fast this moves. When you get really fast edges, you'll have low amplitude signals typically. Not all the time, but typically. So like my Type 106, which I use in a lot of videos, it'll do 120 volt square waves, but if you put a 50 ohm terminator on it to get as fast a rise time as you can out of it, It will do 12 nanosecond square waves, but it won't do it at 50 ohms. And we'll show that on the DSA because it's more than capable of reading that. Also, the fast edges are, so the fast rise, fast fall. Fast falls, it's just the inverse. It's coming from a high to a low. The fast rise and fast falls are 1 nanosecond signals. Decently fast. Reasonable for calibrating an oscilloscope, at least a slow one. Not a 475 or even a 485. And it kind of run at 1 nanosecond, it kind of runs out of gas on even some of the slower 7000 series plugins. But it only does 500 millivolts into 50 ohms. So we have speed, but we don't have amplitude. A lot of the times where we get a lot of amplitude, we're slower. And that just has to deal with physics, parasitic capacitances, and all kinds of real world problems that we have to deal with in non-math situations, but bringing things to life on the bench. So the 106 is 12 nanoseconds. The 106 fast rise is 1 nanosecond. And it should be noted that especially with like the 284 and things like that, it generates signals that actually are too fast for a BNC cable. The 284 at 70 picoseconds can get to 5 gigahertz, which actually overranges even fast BNC cables, because BNC is typically only good for about 40 megahertz. Or, sorry, 4 gigahertz. 40 megahertz. Okay, this looks pretty good. So now we'll stretch out the waveform a bit. And this doesn't look too bad. And let's do... That's not what I want. We want to measure. Fast fall's measuring here, but I don't want fast fall. I want measurements. Take that off, and I want rise. So now what we can do is we are triggering on the negative. So I actually want to trigger on the positive. And we'll measure. And let's stretch this out a bit. Will it give me a rise time, or do I have enough waveform? I may not have enough waveform. I had to argue with this for a bit. So we can see all the odd harmonics in the FFT. I'll speed this up by going to my fast rise, which will be here. If I can get this on this connector. Let's see, waveform. And page to single waveform. And we'll auto set this. That didn't work. Okay, here's the rise time on the slow side. This is a low amplitude signal, so it doesn't short out the plug-in. What I'm going to do is I'm going to take the output, move it over to the fast rise side. And we'll kick this back over. Not adjusting any... Actually, no, I can't do both at the same time on that one because of the switch. But you can see how much steeper the line is. And this is even saying it's 8-ish nanoseconds, but it's got a question mark because it doesn't even know. So if we expand out the time base, make this run a bit faster. Let it build the averages. But we go from 8 nanoseconds to 700 picoseconds on the fast edge. So the important part also with this fast edge is this transition is as clean. Turn off the touch panel. This transition is as clean as possible into a flat top waveform. So you want it to, for doing a scope calibration, you want it to pop up, flatten off, and then stay flat. This is also why I have to use several different calibrators when I'm doing an oscilloscope, is because this gets me a decently fast edge, but then I have to use the tunnel diode pulsar. Problem with the tunnel diode pulsar is it doesn't stay flat after 20 nanoseconds. It climbs up till the waveform brings it back down. So I get a fast pulse and a good settle, but I don't get a decent long-term stability on the square wave. Where will this cause someone to struggle during a scope alignment? If you're using a square wave that's too slow, you can't do the high frequency side of the plug-in alignment or scope alignment for a 400 series. My personal recommendation would be, if it looks good, don't adjust the HF compensation. It's very easy to get that out of alignment, and it's hard to get that back into alignment. And if that's out, the bandwidth, the measured bandwidth of the scope channel will be affected. So one thing you can do to see how your high frequency is looking is shoot the fastest square wave that you have available to you into the front end of the scope. If that looks relatively good, hit it with a sine wave and do a bandwidth check. If the bandwidth is there, until you can get a fast edge signal that is capable of analyzing and measuring the scope, just let it be. If not, you'll be chasing bandwidth for a while. So for function generators, this parameter of their square wave functions, some of them don't even spec it. Some will say 1 nanosecond, tens of nanoseconds, 15 nanoseconds. I think the one Siglent I found was at least in the picoseconds, but it was high picoseconds. It was 3 digits. Now, this is not to say, this has nothing to do with duty cycle or rep rate of the square wave. Rep rate is the pulse chain, how fast the square waves are coming. Nothing to do with that. You can have a 10 hertz square wave with a very fast rise time. You still have a very fast square wave. You have to treat that like a very high, well, for example, if you had a 10 hertz square wave with a 70 picosecond edge, you have to treat that like a 5 gigahertz signal, not as a 10 hertz signal. So rep rate is not edge speed. Edge speed also gets into some board design, high-speed digital communication, things like that. I forget what the part number is now, but there was a time where somebody, a manufacturer, just increased the edge speed of an IC, and it caused people to have to redo boards. They started failing because they had like a 10 nanosecond edge speed, and now all of a sudden they have a 50 picosecond edge speed, and it was actually causing boards to crash. So edge speed, the rabbit hole is very deep and very windy, and I haven't found the bottom yet because I'm still trying to align the 284. Okay, let's take a look at some of these edges in the analog world. So we can zoom this in, and if I was looking at the scope, I'd be interested in this front edge right here. That noise you see in the trace, like right there, that's the readout. If I turn the readout off, that goes away. So what we're going to do is we're going to take the time base and we're just going to crank it out. And obviously, because I'm speeding it up, the brightness has to come up. And since we're running very slow, let's turn the rep rate up so the scope gets happier. Keep going. So we can see it comes up and then kind of settles off. So this is a slow plug-in, but we're also at 5 nanoseconds per division. So if I'm tuning for 5 nanoseconds, this 800 picosecond square wave is just fine. I just have to tune this front end. And this is a slower plug-in. Let's move over to the 7854 and we'll take a look at this waveform on a 500 megahertz plug-in in a 400 megahertz frame. So we're going to be limited in bandwidth to the frame, but we'll take a look at it a little bit quicker. Okay, we are on the 7854. And we'll bring this up. Crank this out. Now I'm going to have to put the viewing hood on because the camera's not picking this up so hot. But that is because, it is a very fast signal. So we have the same signal, but now we have a little bit of aberration here in the front. That's okay. This is just that tuning. This is when you do that RC high frequency compensation adjustment. This is what you're kind of tuning. I would bring this up, probably bring that down a little bit, bring this up. Some of these adjustments would do all of those, and that would allow to get the fast edge with the best flat top. This isn't bad, especially because I'm limited in bandwidth by the frame. So this is not unacceptable, even though it's got a little bit in the front. We can see the just difference in wave shape if I switch over to I'll do the right side, channel 1 DC and 0.1. Just by switching plugins, now we're a little high on this side, a little low over here. This is now a 200 megahertz plug-in, but it would pass background checks. So it doesn't have to be perfect, but you don't want a whole bunch of ringing here when it bouncing around. The reason moving from a 1 kilohertz to a 10 kilohertz signal brightened up the trace on the scope is because I was pushing these scopes very close to the tube's writing rate, which is another limitation of the analog scopes. The beam can sweep as fast as it wants. The phosphor may not absorb enough energy to get bright enough to see, so that's where some of the acceleration voltages come in, especially the higher scopes where they get the microchannel plate CRTs. There was a lot to do to get the writing rate up to look at the faster signals, especially when it came time for some of the more exotic projects that were worked on during this era. So what I did was I kicked it from a 1 kilohertz signal to a 10 kilohertz signal. It let the trigger hit faster, so the scope was able to brighten up the trace. So I hope that cleared some things up. If anybody has any questions or comments, please leave them below in the comment section. I do check all the comments, and if enough people ask, it can lead to a video, which is how we got here. So thanks again for dropping by. I will see everybody in the next video. More is always on the way.